2. All right, so you already read your does cold exist. That's the question of the day. Does cold exist? No. What exists? Hold on. So cold is an absence of heat. Well, what is heat? What is heat? Kinetic energy. It's just a lot of kinetic energy, right? So if something has very little kinetic energy, its temperature would likely be low. And if something had a lot of kinetic energy, its temperature would be high, right? I don't say hot and cold, because they high and low. All right, so that's kind of just like the general rule of thumb, right? So what you're going to notice now, and this is the big idea, between gases to thermochemistry, we actually are going to change temperature units. Okay, so in gases, we always took, what is our temperature unit? Kelvin, 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 Kelvin. Anytime you use the gas law, you have to use Kelvin, without a doubt. Now we're going to start to get into thermochemistry, and with that comes some new equations like Q equals MCAT that we spoke of yesterday, Q equals moles times delta H fusion, things like that. And we actually have to use Celsius. So when you're doing gas law problems, you use Kelvin. When you're using thermochemistry problems, which is going to be very apparent, it's going to say heat, heat, heat. That's going to be when you use Celsius. So we're going to kind of maybe diverge our minds in that mindset. All right, so up here, what's the rule about how energy is transferred between two objects that are in contact? John, give me something. Not waiting. Cassie. Okay, so the law of conservation of energy comes into play, so neither created nor destroyed, but tell me how it is transferred when they are in contact. Like, how do you determine the way it's transferred, Ashton?
It said it transfers from high to low until we reach neutral.
Right, okay, so this is going to be true always, because we will never lose energy because the energy is simply transferred. So when we say law of conservation of energy, it just means that it's transferred from point A to point B. And when it is transferred from point A to point B, it's going to go from the high kinetic energy area to the lower kinetic energy area until, what's the word that means equal? And put that together with heat. Thermal equilibrium, right, until thermal equilibrium. That just basically means it's at the same temperature from point A to point B. So you're holding your ice cold frosty from Wendy's or something in your hand. Where's the energy being transferred? Yes, from your warm hands to the cold frosty until when? Okay, so until your hand is so cold, but the ice cream frosty has warmed up. They're at the same temperature. Now that would be very uncomfortable for your hand because it would get quite cold. But with that respect, you can also go the other way. If I'm holding a nice hot beverage and I'm holding it in my hand, where does the energy get transferred? To your hand from the hot beverage. Now that also could get very uncomfortable. So there's temperature sensors in our hand that tell us like, hey, drop that, it's gonna burn you, or hey, that's gonna give you frostbite and basically burn your hands off. Okay, so all particles have the same kinetic energy. Yay or nay? I need a survey now. Yay or nay? Oh, overwhelming nay. Okay, all particles have the same kinetic energy. So we kind of saw this in our gas law stuff. Let me kind of draw this picture like right here. Remember you had like little particles drawing like this? And they had different size arrows. What were the different arrows indicating?
Slower, faster.
Some things are slower, some things are faster. So what you can say is that at a given temperature, all of them have the same average kinetic energy. So when we start to average things at the same temperature, that average is kind of the point we look at, and that's what we say is the same. So if I've got particle A at 20 degrees Celsius and particle B is at 20 degrees Celsius, particle A and B's are totally different things, but they can still move at these different rates. However, overall, the average is the same. So no, not all particles of a substance have the same kinetic energy because their average is the same, but the individual particles may not. So that's more false than true. Definition of temperature, kind of just said it. Let's go with somebody back here. Caleb's area. Definition of temperature.
He said that temperature is the movement of particles changing at constant increase.
Give me simpler. Simpler. Kato's got you. Okay, measure of heat in a substance. Okay, so measure of heat might be simpler. I was also going to say just average kinetic energy. Temperature is average kinetic energy. So they are similar in that respect. Name 3 types of motion. Kaylin, give me one.
Translation.
Translation. Okay. And then another one, Lauren.
I need to get this one.
Look in your stuff. I'm coming right back to you. Bradley, where's this at in the reading? Yeah, it's on the first page. So if you guys were working on something else, that's on you. I need something from this table. Frank's table. William, I need 2 more from you guys.
Rotate.
Oh, sorry. William, and then give me Will's table. Rotation. So translation, rotation, and somebody else at that table.
Vibration.
Thank you. Wonderful. So we can see that kinetic energy comes in 3 flavors. Translating, so things moving left to right, rotating like a microwave, and then vibrating, which is basically how a microwave works. It causes your particles to vibrate with high frequency, which means they get really hot. That's actually how a microwave works. It just speeds up the vibrations of the molecules. All right, so then going down to number 9 now. What is a heat, or draw a heat curve and then label. So this is where some people were wondering what specifically to label. So here we go. So William, tell me. Sorry, my mouse is now not allowing me to work. Okay, so tell me how to draw that heat curve. Hold on, I gotta get my axes. Hold on. So, what are my axes?
That's going to your y-axis is your temperature, which is the substance.
Right, and so that's only because we're dealing with what here? Heat in thermochemistry, not gases. And then this one?
Your x-axis is your time.
Time or what?
Time or...
So it's like time passed as energy is supplied. So you can say, you could say, now I'm going to put kinetic energy more correlating with temperature. So I don't want to add that there. There's another word I used. I drew this yesterday too. Anybody? Heat added. Okay, so time is just, of course, always going to be correlation. And so heat added is like over time, as I add heat, what does that do to the temperature of that substance in particular? And it really just makes you notice that heat and temperature are 2 different things, which is why we can label them differently. Syrian, pick up from here. How do I draw the heat curve? Okay. Uh-huh. Okay, and then Brandon, tell me about the motion of particles at each segment.
Oh, okay. Start with solid.
Gas. So he's going to say solid, liquid, and gas. We start to notice how to label those with the phases of matter. And tell me about the motion here.
So solid is like the molecules are really packed together.
Okay, so I'm just going to label these 1, 2, 3, 4, 5, 6. It's a little easier to speak from a point. Okay, so at point 1, what's happening with the motion of particles?
They're really slow.
Okay, so I'm going to say almost no movement. So they're moving really slow. And that might be at, like, let's just say negative 200 degrees Celsius, something pretty low, so it makes sense. But they have no, or basically lowest kinetic energy we can get. So they're very slow in their movement. What about point 3, Frank?
That is very or well.
So you can tell me about, so tell me about the motion.
It's trying to move faster.
Okay, so I'm going to say like medium movement. It's moving a little bit faster. And then, of course, let's say 6. Lauren, pick up from there. What's going to happen there?
It's moving extremely.
Right, so extremely fast movement. And that should correlate with what other variable here that correlates with kinetic energy, Isabella? Right, and so as we went from 1 to 3 to 6, we went higher and higher in temperature, which is what's correlating with our movement. So related to that, now you could sketch these particles. So as a solid, they'd be compact, liquid, they'd be farther apart, gases, they're super, super, super far apart. So noting that, you know, like close, a little bit farther away, and then like, there's our gas. Tell me about the intermolecular forces at play here, Avery. Like, explain what intermolecular forces have to do with these states of matter. Here's my first state of matter. Kind of compacted solid, and then a little bit more spread out liquid, and then like gas. Good. So let me actually abbreviate that. IMFs are strongest in the what? And why? Right, and I'm going to elaborate on that. But they're close because, do they have a lot of kinetic energy? So are they able to like move away from each other? No. So IMFs are strongest in the solid because low kinetic energy, so increased forces of attraction, just simply because they can't move away from one another, so their forces stay very quite strong, like magnets holding them closer. But as things start to move and get more kinetic energy, they start to move apart. Caleb, pick your head up and go stand up. Don't be rude. Go stand up. And then your correlation of IMFs do correlate with kinetic energy motion here. Yes, ma'am.
So it's like the point number 3 actually the melting point, like point number 3 is
Point.
Like,
So 2 and 3 are the actual melting point, as in the temperature melting point right here of the solid, right? So 2 and 3 are at the same temperature. But what you'll notice is at 2 you have mostly solid, but over the course of this little plateau, your solid starts to morph into liquid, so it starts to melt, and so at point 3 you have all liquid, and then that all liquid starts to heat up.
so
Okay.
it's the same temperature,
It's just over the course of heat being added, and as that heat is added, temperature is not being influenced, and that's because of phase changes. Temperature doesn't change, and that's due to the potential energy being changed, not the kinetic energy being changed. We'll elaborate more with that. Okay, so any questions on this so far, guys? Who feels okay with heat so far? Kind of nice because it goes back with phase changes, which we learned a couple weeks ago. All right, so go to my website, and under the website, I want you to pick up where you left off from yesterday with the thermochemistry web test. I'm going to come around and see your annotations, and I'm going to come around and see that you did your warm-up with me like I asked you to, and then I should be able to give you your paper back pretty immediately. So have that out for me. Thanks, dears. Looking at it now, I'm that waitress who's going to forget your order. And what you've noticed already is that you start to see this Q equals MCAT or Q equals MC delta T quite a bit, right? Well, one of the ideas is how does the law of conservation of law of conservation of energy play into that equation? So that hand in the coffee cup example again. So I've got my coffee cup. It's hot, right? Where is it transferring the energy? To my hand. Okay, so the heat from this coffee cup is being lost to my hand. Okay, so this Q, this heat from the coffee cup, would you express it as a positive Q or a negative Q as it is being lost from the cup? Negative, because itself is losing energy. So we say that's like a negative sign as to indicate the lost heat. But my hand is what? Positive, because it's gaining energy. So that idea is going to play into how do we relate heat and heat, because it's the same heat. It's just being transferred from one place to another. So here, let me start here for a second. Note to self, I'm going to kind of just do a little hand. Okay, touch the body. There we go. So this is my coffee cup, and that's going to be a negative Q because of the exothermic nature or the loss of energy from this coffee cup. But then my hand over here, this is going to have a positive Q because it's an endothermic process, meaning it's gaining energy, but it's the same energy. So aren't these two values of Q and Q equal to each other? Isn't that Q, that heat? That's the same heat, the energy that's the same energy the hand is absorbing. It's the same exact value. So let's say the cup of the water or the cup of coffee lost 100 joules of energy. Well, it gave it that same energy, 100 joules, to your hand. So the Q, or the energy that's exchanged, is the same. It's just when we identify a negative and a positive, we're just identifying the fact that it was lost or gained. You with me so far? Okay, so as we note that, this Q equals MC delta T for the cup can be set equal to the Q of your hand, or the Q, the heat that your hand is absorbing, because they're the same thing. Well, if I can set Q equal to Q, cup and hand, I can set the stuff that Q equals to the stuff that Q equals. So I can set MCAT equals to MCAT. You got me? Because it's the same thing. So I can say MC delta T of the cup equals MC delta T of my hand if I had a mass of my hand and specific heat capacity of my hand and delta T of my hand. So I could do all that. So that's really the scenario here, is that we're talking about the law of conservation of energy. So they're doing this based on water and a metal, because this hot metal is being dropped into some water, and then from there we're going to calculate the overall specific heat, which is C, specific heat capacity of metal X or metal Y. So you'll notice that they give you a couple variables up top, that the specific heat capacity for water, and you need to write this down for yourself right now, is 4.18 joules per gram degree C. C of water. And I'm going to erase this, but I don't want to. I need another board. I need aluminum cans for a lab we're burning food. Okay, we're going to burn food like on Tuesday. So I need aluminum cans, so note yourself in your phone or something, set a reminder. Aluminum cans, if you have any, please, PG or rated G ones. Like, I don't want other ones. And then this is the link. Oh, right that back on the board later. It's for teaching type. Okay. So here we go. See, I'm going to actually label this water and metal, and this is going to be how you would identify or organize your work. Can you guys see that blue?
Yeah. Yes.
Okay, so the C of water is 4.18 joules per gram degree C. All right, so that's what we know so far. Remember, we're in Celsius. Remember, the heat gained by the water equals heat lost. Okie dokie. So back to my simulation. Here, let's choose a metal. I'm going to choose metal X. And I'm going to call it 20 grams of metal X. And I'm going to start it off at 20 degrees C because that's what it kind of indicates to me. Now, my water, I'm going to keep at 30 grams. So I got a lot of givens already. So I'm keeping actually the default simulation data. So my metal has a mass of 20 grams, right? And it has a temperature initial, so TI, temperature initial of 20 degrees Celsius. But then I look down here at water, and I can see my mass of water is 30. M is equal to 30 grams. You guys still see that blue? It's looking okay. All right, but notice my two temperatures are the same. Are they going to exchange heat? They're already at thermal equilibrium, right? they're not going to exchange heat. So let's make that, let's make that metal hot. I'm going to leave my water at 20. I'll move my metal. I'm going to make it 150 degrees Celsius initial. So I'm going to change this temperature initial of metal to be 150. What's my temperature initial of water? What's my temperature initial of water? 20 degrees Celsius, because that's what the simulation says. All right, so now that they're at different temperatures, this will work. So all I have to do is hit start. It's going to kind of start the reaction. The hot metal's going in. Notice what's happening to the water temperature. It's increasing. Why? So the metal is hotter than water, and it is transferring energy to the water, which is reflected as a increase in temperature. Alrighty, I think it's done, so you guys can run this exactly the way I am. And you'll notice the metal and the water, thermal equilibrium is met. So that means they both end at the exact same temperature, because if they haven't met the same temperature, we're not done yet. And so we assume that they both are now at 29, okay, it's starting to cool down, but 29.77, stopping there. T final is 29.77 degrees Celsius. And T final is 29.77 degrees Celsius, simply because they have to stop at the same temperature. All right, what am I missing in terms of variables here? Well, I can calculate my delta T's, right? I got two temperatures. I can calculate delta T. What else am I missing? Specific heat of what? Because that's what we're solving for. That's what the question asked for. So in this case, no. Okay, so you guys have MCAT equals MCAT. Use this data, set it up, solve for this T metal. Well, you set up your variables first and go plug them first. Yes, sir. I got you. I told my kids to fix that up there in the lunchtime this morning, so you're good. You okay? I saw the 3 a.m. email, so. You good? I'm sorry. I'll fix it back. All right, so what I meant by that, and I'm sure you knew, but here we go. I'm going to say this one, I'm going to just rewrite this, MC delta T equals MC delta T. Let's call this one water, because I can identify all the water stuff like I have on the board over there. And I'm going to call this one metal, for M for metal. Who is losing energy, metal or water? Metal, so who gets the negative? The metal. So I'm going to put a negative sign out here so that you can see that it's showing the loss of energy. Who gets the positive? Water, so H2O. Alrighty, so now I have everything I need. Which of these variables am I solving for right here? Specific heat of the metal. So right here, I'm solving for this guy right here. Isolate it. What do I got to do? Divide by, and not only just M and delta T, but the negative as well, right? So negative math. Got it. Dividing by negative M delta T. Dividing by negative M delta T. Okay, that mass, whatever the metal, the mass of the metal is going to cancel, and the delta T of the metal, it will cancel, and that negative will cancel. That leaves me with C of the metal. All right, I'm in business now. I'm not done with my calculation. I'm just setting up the variables, so when I plug them in, I'm good. So all that stuff allows for C to be isolated by itself. And this is specific heat capacity of metal X. Now, I have MC delta T divided by M and delta T. How do I know which is which? Because one's regarding what? Like, how do I know what that M is? Like, that's metal of what? I mean, a mass of what?
Water.
Of the water. And so I know now, I go back over here, oh, water weighed what? 30 grams. All right, so I'm going to put that on top, 30 grams. And my specific heat of water, it told me the problem was what? 4.18. This is where we have a big unit again. Joules per gram degree Celsius. Okay, and then what's my delta T? Remember, how do you find delta T? It told you in the simulation. T final minus T initial. So I'm doing the difference. So 29.77 minus 20 is what? 9.77. 9.77 degrees Celsius because I did T final minus T initial. Okay, all of that is MC and delta T. Done. Almost. That's just the numerator. Now I'm going to divide it by what? The metal, right? Everything regarding the metal. Okay, so the mass of the metal was what? 20, right? There's a lot of data here, but if you organize it in a data chart, kind of like we did over here, you are awesome. Okay, and I will also divide by what? How do I find the difference in this metal? Yes, you have to do what? Brandon?
29.77 minus 150.
Yes, T final, 29.77 minus 150. Do that in calculator. What is it?
Negative 120.23.
One more time. Thank you. It is negative, and I'll tell you why the negative matters. So negative 1 what?
20.23.
Okay. So this is negative. Now, what did I not carry with me, but you know I need to? This negative right here, right? So that negative hanging out here, basically just what? Makes everything positive. And specific heat capacity is a value that's an internal kind of characteristic. It's always positive. Everything's always positive except for one of those temperatures, because one will drop and one will rise. So now that I can see that negative and negative is going to cancel out, I kind of just ignore them because I know how to put this in my calculator now. Put this numerator in your calculator, calculate. Go for it now. We don't have a lot of time. 7 minutes. Anybody? Say again? Did you do just the numerator for me first?
Oh, no.
Can I get a numerator? 1,016? Okay, sorry, 15816. Alright, so I need to know what unit that is. So I see grams and grams cancel. Delta C, or degree C and degree C cancel. So I heard joules. I don't know who said it, but thank you. That is joules. Now we're going to divide that by whatever this is multiplied by each other. What is that? 2,404.6. And what unit is that? Grams and degrees Celsius. Grams times degrees Celsius. Guess what joules divided by grams degrees Celsius is supposed to represent? Specific heat capacity. It's just a weird unit, like the R unit was in gases. This is the weird unit in thermochemistry. So now calculate, for real calculate. I think that's what Cassie, you were trying to tell me. What is it? 0.5095 joules per gram degree C, because none of those units at the end will cancel. And yes, we will look back and see sig figs probably need 3, so let's round that to what? 0.510 joules per gram degree C. Yeah, I usually say joules per, by what I mean by that is divide, grams degree C. Yeah. All right, so here's my last thought, and then we have to pack up, okay? So my goal is for you to finish up this over the weekend. Your webbook will be due Monday. However, we have intervention on Monday, so if you choose to do CK12 stuff, I get it. If you want to do this, I get it. Part 5 is an energy efficiency of your home, so that is something you probably should think about at home, because you can kind of walk around your house and think about it. But because we're burning food to actually calculate calories that are inside of that food. For the weekend, Friday, Saturday, Sunday, hold on, let me pull this up on my website. I have it as Friday, Saturday, Sunday. Monday. So this will be due on Tuesday. You are going to track what you eat for 4 days. Okay? And I need to know that because we're going to look and see what kind of calorie intake versus fat, carbs, proteins. Because when we burn our food, I actually want you to be able to reflect back on a specific food you ate. So if I'm just giving you marshmallows, you're like, I eat marshmallows daily? No. Okay, so we're going to look at something you actually eat. So listen, this isn't a super duper easy assignment. I got 4 minutes, so look up here. So it's a 4-day nutrition journal, and you can either download an app on your phone, MyFitnessPal, or like Lose It. There's lots of like nutrition tracking devices on your phone, and you can also do it on the computer. It doesn't have to be an app. I know you guys like you run real low on space on your phone, but I need it for 4 days. When you make an account, it's going to have you create probably like a little profile, but here's your point values. You get 10 points for just creating an account. It doesn't have to be with MyFitnessPal. It can be with another one similar to that, but it's just something that can track your food because it's easy for you to go back and look at your carbs, proteins, fats, and other nutrients that way. So that's almost half the battle. Complete the accurate record of food and drink intake. So it's 10 points a day. Friday, today, Saturday, Sunday, Monday. Okay, so try to think of everything you consume, even if it's a packet of mustard, okay, that you put on a sandwich, or some creamer you put in coffee, or something like that. At the end, it says reflection. So at the end, this is kind of what I'm looking for is you know what your nutrition goals were, you're kind of reflecting. This gets you set up. You don't have to track your fitness. You don't have to track your exercise, but that's a lot of times an option on there. So dancing at prom, you can count that for 3 hours or whatever. I don't want to know more. And then here's your reflection component. This is half of the point. So the first half is just like, I've done it, I'm done. The second part is thinking about what did your recommended caloric intake reflect, and did you eat too many calories, did you eat too few calories, kind of just reflecting on these nutrition values in itself. After that, did you meet your nutrient goals? What kind of insight did you take in? And then describe 6 separate accounts of chemistry that will give you full credit for, basically write a healthy paragraph on how this assignment relates to chemistry. Don't be shy. Give me 6 healthy things, and that'll give you 30 points for that individual question. That's the most important question, let's be honest, okay? So this is on my website. I'll give you a chance to ask me questions on Monday too as well. And I'll try to make it very clear. There's a couple of things you could be asking me questions on, but basically track your intake, reflect. Laptops up. No, I checked it for completion. You're good. This is due Tuesday. You're tracking for 4 days.
Okay, so what's the other thing?
CK12, if I need to give you more time on, I can. Okay? Is that what? Yes, thank you.
Let me put in the box.
Yes, ma'am.
Yes, please, more time. I appreciate it.
Okay, let me, I'll update the website to be more time. I just don't know what day it'll be at. Okay. I'm finding out that it was longer, and it took us longer than I thought it would, so. Thermo Solutions Equilibrium. So we're in Thermo Solutions and Equilibrium will be our last 2. Yeah.
And I saw you have an honors paper.
Where do you see an honors paper?
On your website, the honors paper section.
Yes, and I'm just going to do a portfolio. I change every year. I used to do Mythbusters all the time, but I didn't do it last semester, so I couldn't do it this semester to keep the nature of the course the same for that grade level or that year. So at the end we'll do an e-portfolio that reflects on our different objectives. I'm still working on the details of that because it's kind of like a reflection. Yeah. So you'll find artifacts of learning. You'll find artifacts of critical dialogue, which your close readings are great for that. You'll upload a reflection on ways that you've now found in real life, things that relate to chemistry, things like that. Yeah.
I was a teacher. You have an abstract or something.
You guys, it's
Your abstract together.
yeah, and this course is so naturally honors. A lot of teachers are like, well, aren't you doing a paper? Aren't you doing they've already done a lot. They don't need to do just a paper because they think you do papers. So a reflection in itself, as long as I can see some critical thought.
Yeah, I thought it was really cool because I was watching this TV show and I thought it was so cool.